Hi everybody. Let's do solutions to today's problem set. So these first couple hopefully will build on each other and start simple and let you really practice with the ideas. So one thing we know is that if the function was 1 over x, then the domain would be x not equal to 0, because 1 divided by 0, indeed, any number divided by 0 is undefined. You could also know that by thinking about the shape of the graph. Looks like this. And there's a vertical asymptote at 0, no defined value. So that would be 1 over x, but we don't have 1 over x. We have 1 over x plus 7. So two ways of thinking about that. One would be that we've left shifted 1 over x by 7. So you could imagine it graphically as like this. So now the asymptote that used to be at x equals 0 is now located at negative 7, which would mean that the domain is x not equal to negative 7. A different way of thinking about it is, you know that whenever you have 1 over blob, 1 over anything, what must be true is that that blob can't equal 0. So here we've got x plus 7 as our blob. And so now you can solve this inequality. What value of x, so if x plus 7 doesn't equal 0, what value of x can't equal 0? And the answer is, or rather, what can't x equal? So if I subtract 7 from both sides, we also get x not equal to 7. So you can think about it graphically, or you could set up an equation. I know the denominator can't be 0, so let's write that down, denominator not equal to 0, and then solve for x to say what can't x be equal to. All right, let's build on these ideas. So for part B, 2 to the x, you can also think about graphically. We see here that no matter what the x value is, it gets a valid output. So the domain is all real numbers, which you can also write this way, x member of the set of the reals. Or you could think about it numerically. You know that 2 to the power of anything is still a well-defined value. If you plug in negative numbers, that would be like saying 1 divided by 2 to that power. Positive numbers work. 2 to the 0 equals 1. So you can think about it graphically or numerically, but the answer is the domain is all real values. Okay, what about part C? So here's A, here's B. For part C, we've got what's the domain of root 5 minus 2x. So here we can use that same kind of blob technique. I know that whatever is inside the square root has to be positive in order for the output to be a real valued number. So let's set up an equation and solve for it. I've got 5 minus 2x greater than or equal to 0. We'll add 2x to both sides. We'll divide by 2. So x less than or equal to 5 halves. All right, let's do part D. Part D, this is the first time we have to start putting things together. So here we've got a function that's root 2 plus x in the numerator and x minus 10 in the denominator. So there's two separate things that cause us to have to restrict the domain. We've got a 1 over something, and we've got a root something. So for the root something, I know that what's inside the root has to be positive. So what that means is that negative x is greater than, well, maybe let's not do it algebraically. Let's just think about it logically. If 2 plus x has to be positive, or at least non-negative, then the smallest thing x can be is negative 2. So x has to be greater than or equal to negative 2. And you can just double check that by imagining, what if x was smaller than negative 2? What if it was negative 2.5? In that case, 2 plus negative 2.5, it's not greater than 0, greater than or equal to 0. So just the inside of the root has led to this part, but we're not done yet, because imagine we plugged in x equals 10. In the numerator, we'd have square root 12. That's fine, that's a number. But in the denominator, we'd have 10 minus 10 is 0. So that would not produce a valid output, which means 10 is not in the domain. So if we're going to think about it kind of systematically, I know that the denominator can't be 0. So x minus 10 can't be 0, which means that x can't be positive 10. And so the domain is both of those put together. So you could just write that. You could just write that the domain is x greater than or equal to negative 2 and not equal to 10. So all of that together is the domain. All right, part E, all we've done is flip the numerator and the denominator. So now I've got x minus 10 in the numerator and root 2 plus x in the denominator. So what's changed? Now it's totally fine to plug in x equals 10. Let's look what happens. If I plug in 10, I get 0 in the numerator, and in the denominator I have root 12. 0 divided by root 12 is just 0, so that's fine. No problem there. So the only thing we have to pay attention to is the denominator. So I know from the root, this is the same as last time. I know that 2 plus x has to be positive, which still leads to x has to be greater than or equal to negative 2. There's one additional thing, though. I know that the entire denominator, this root 2 plus x, this whole thing can't be 0. So what value of x would make this 0? Because that's the value of x that wouldn't be allowed. If x equals negative 2, then I have root 0, which is just 0. Or you could solve it algebraically by squaring both sides and then subtracting 2 from both sides. But we also have that x can't be negative 2. Rather than putting a box around both together, think about combining them more logically. If we're saying x has to be larger than or equal to negative 2, but it can't be equal to negative 2, what we're really saying is x has to be larger than negative 2. So don't write it like this. If you're able to combine several different restrictions together in a logical way, then please do so. All right, let's go on to f. So f, we've got ninth root x minus 1. So this one we could think about graphically. I know that the parent function is ninth root x, and I know that has a shape that kind of looks like this. It's one of those root shapes. What about the negative 1? Well, the negative 1's on the inside, which means I've just right shifted it by 1. So based on this picture, I can just immediately say that the domain is all real numbers. I can plug in any x value, even negative x values, and still get a valid output. So I think that would be a great way to address that one. Let's do G. This is another problem where we have to look at all of the different parts. So the square root x, we know, has the restriction that x must be greater than or equal to 0. This produces its own restrictions, though. So I know that the denominator can't be can't be 0. So you could write an equation, or you could just think about it logically. If I know that this can't be 0, the two values that might make it 0 are 1 or 2. If I plugged in 1, I'd have 0 times something, which is 0. If I plugged in 2, I'd have 2 minus 1 is 1 times 0 is still 0. So this produces x not equal to 1 or 2. So this is a case where you can combine them together. X is greater than or equal to 0, and also it's not 1 and not 2. All right, let's do the last one in this section is h. So h, we've got root x squared plus 1. So what I know is that x squared plus 1 must be positive. And without any further work, I realize this always has to be positive. Because no matter what x is, squaring it is going to make it positive. So the very smallest thing this could ever be is 0. And then I add 1 to it. So the minimum value of this right here is 1, and that's greater than or equal to 0. So kind of thinking about it numerically, I can conclude that x is a member of the set of the reals, or the domain is all real numbers. All right, let's do the next set. So it says, sketch a rough graph of f of x equals x minus 1 over x minus 1. Okay, well, looking at it, maybe you don't think, aha, I know what shape that is. But you can think about substituting values. So if x is like negative 10, I have negative 11 over negative 11, which is 1. If I have negative 1, that would be negative 2 over negative 2, which is 1. If I have really anything at all, it seems like the output is going to be 1. So it might seem like the graph looks like this. It's just the horizontal line at y equals 1. Except for one thing. If I substitute x equals 1, then I get 0 over 0, which is not a defined value. So that means that 1 is not in the domain of the function. So the function equals 1 everywhere except for an input of 1 where it's not defined. So it might be tempting. So now I'm going to talk about the note, like this note down here. So it might be tempting to rewrite this equation and say, well, f of x is really just this. F of x equals 1. It's the horizontal line at 1. And while these two are algebraically equivalent, the functions aren't the same function, because saying f of x equals 1 corresponds to this function, which is defined everywhere. Saying f of x is x minus 1 divided by itself corresponds to this function, which has a hole. So the lesson of this part is you're allowed to do simplifications, but if the simplification ends up eliminating a hole that was there, you have to add it back in with a domain restriction. So you could say f of x equals 1 for all x not equal to 1. And that's saying the output is always 1 as long as x doesn't equal 1, and that puts back in the hole at 1. It's called a domain restriction. It's a statement that you make to make sure that your function is actually equivalent after you do a simplification. So if we're going to apply that idea, let's do 1b now. I've got a function g of x is x plus 3 squared over x plus 3. It seems like I could cancel one of the x plus 3's on the top with an x plus 3 on the bottom. I could divide them out. So it seems like this is equal to just x plus 3. Except in the original, I can't use x as negative 3, because that would make 0 divided by 0. So I can rewrite g of x by saying g of x is just x plus 3 for all x not equal to negative 3. And so now I've simplified my original function and added a domain restriction so that the new simplified function has the same domain as the original function. All right, let's do the good ones here in number 2. So here I said, based on 0d above, I could visually show the domain on a number line. So the domain of root 2 plus x divided by x minus 10, remember we'd said it was x greater than or equal to negative 2 and also x not equal to 10. And so you can notate it this way. Closed circle means that we're including the negative 2, and then it's all shaded up to infinity except there's a hole at positive 10. So that would be the same domain restriction, but shown graphically. So let's try 2a. We've got root 6 minus x plus root x minus 4 divided by x squared minus 25. All right, so we've got 3 things we have to pay attention to. I know that 6 minus x has to be positive. I know that x minus 4 has to be positive. And I know that x squared minus 25 can't be 0, because the denominator can't be 0. Okay, so let's see what each piece here implies. So here I've got that x has to be smaller than or equal to 6, because if you imagine it's larger than 6, 6 minus something larger than 6 would make that negative. So that's where that part of the domain comes from. But it's also true that x has to be greater than or equal to 4. So x is between 4 and 6. And again, let's imagine what happens if x is smaller than 4, like if x was 3. If x is 3, then I'll have 3 minus 4 produces a negative under the root, and so we don't have a real valued output. All right, what about the denominator here? You might recognize this as a difference of squares, so you could factor this as x plus 5 times x minus 5 not equal to 0. If you didn't recognize it as a difference of squares, that's okay. You could get the same answer just by solving it like a quadratic. So I'll add 25 to both sides. I've got x squared not equal to 25. I'll take the square root of both sides, giving me x not equal to 5 or negative 5. here also you can see the same result. If I plugged in 5, that would make this factor 0. If I plugged in -5, that would make this factor 0. So let's put it all together. I've got that x is between 4 and 6, and x not equal to 5. What about not equal to -5? Well, that's extra. I already know it's not equal to -5 because I know it's got to be larger than 4. So there's no need to write that part all over again. Oh, there we go. Now it's on the screen. So don't write that part all over again. So this would be a great way to write it symbolically. If I'm going to notate it on a number line, I could do 4 to 6. That's all shaded in, except the value at 5, there's going to be a hole right there. So that would be what it looks like. All right, let's do 2b. Here I've got 2 to the x minus 5 to the x over cube root x squared plus 1. Okay, so first let's note that there's no domain restrictions happening in the numerator. It's okay for the numerator to be 0. The domain of 2 to the x and 5 to the x are both all real values. So there's no x that I could plug in up here that would cause either part of this to be undefined. So far we're all okay. What about the denominator? You might be worried about the x and the cube root x. But remember, if this was a square root x, then we'd know that x has to be greater than or equal to 0. But remember, cube root has a domain of all real numbers. So nothing about the cube root causes a domain restriction. What about the fact that the entire denominator has to be not equal to 0? So we could write that. We could say cube root x squared plus 1 not equal to 0. But again, notice it's not possible for this to be equal to 0. The smallest thing this part could possibly be is 0, because we have some number that's getting squared. So if x was 0, 0 squared is going to be 0. If x is anything else, it's going to be larger than 0. And so then 0 plus 1 is automatically positive, greater than 0. So there's no x value that could possibly cause this to be 0. So the conclusion here is that the domain is x is all real values. Okay, let's do the last one. Let's do part C. So to C, we've got p of x is x minus 1 divided by x minus 1 minus 1 over x minus 1. Okay, so first of all, don't get tempted to cancel these, to divide those through, because they don't divide through. They would if that was the only thing in the denominator, but the denominator has another term, and so you can't divide like that. Okay, so let's figure out what does need to happen. So because of that fraction down there, we can immediately know that x can't be 1. Okay, we also know that this entire denominator can't be 0. So let's write an equation for that. I've got x minus 1 minus 1 over x minus 1 can't be 0. So now let's try and solve this. Let's figure out what x value, what can't x equal if this is true. So I'm going to add this to both sides. So now I've got x minus 1 not equal to 1 over x minus 1. Now let's multiply through by the denominator. I'll multiply through by x minus 1. So now I've got x minus 1 squared not equal to 1. Let's expand this out. So that gives me x minus 1 times x minus 1. And if I multiply this out, that gives me x squared minus 2x plus 1 not equal to 1. Oh, I've gone off the bottom. Here we go. So I multiplied through by x minus 1. That's caused this to square. I've written it out. I've multiplied it out. I can subtract 1 from both sides, giving me x squared minus 2x not equal to 0. Now I'll factor the x out. X minus 2 not equal to 0. So what I know is that x can't equal 0 and x can't equal 2. So that's the domain restriction. And I'm putting that together up here with x not equal to 1. You can double check to make sure this makes sense. If I plug in x equals 0, that gives me, let's see, in the denominator I'll have 0 minus 1 is negative 1, minus 1 divided by 0 minus 1 is negative 1. So that's the same as saying negative 1, and then here the negatives become positive, so plus 1, and so that creates 0 in the denominator. So I've verified that the 0 actually does produce 0 in the denominator. You could do the same thing by plugging in 2 and verify that it really does produce a 0 in the denominator. Visually, what that would look like is, here's 0, 1, 2. So our domain is all the values except there's a hole at 0, a hole at 1, and a hole at 2. Note that it's okay to plug in any values between 0 and 1 here. That would be fine. Any values between 1 and 2 would be fine. There's just holes at the integers. All right, I hope that this was helpful.